Hello, everyone. Welcome to Theo-MathProblemSolver. In this particular episode, we are looking at PDE, that is Partial Differential Equations. Now, why do we want to study PDEs? All right, so PDEs, play a very crucial role in various fields such as physics, engineering, economics, and many others. All right, I want to sort of, point out that PDEs are essential for modeling, natural phenomena such as heat conduction, wave propagation, fluid dynamics, and quantum mechanics. But various fields for which we also extend PDEs, especially in relation to population, dynamics, and also in the banking industry, they also sometimes use PDE, especially in the area of option pricing. Okay, option pricing, they also use PDEs as well. So at this point, I would want you to just begin to embrace the concept and the theorem, the definitions around that, and we can leverage those stuff to solve real world problems. Okay. And at this point, if you have not subscribed to my channel, please do so. Like, comment, and share my content to other colleagues who are also having difficulty with mathematics. In fact, the whole goal of this platform is to demystify the myth around mathematics. So let's keep the news spreading. All right. Now, what's a PDE? Okay, what is a PDE? In simple terms, when we talk about PDE, we are saying that it involves some unknown function of several independent variables and its partial derivatives. Okay? Okay, so it involves an unknown function of several independent variables and its partial derivatives. So simple put, so I want to stress that the solution of a PDE, so let me underline some key stuff here. So I want to point out that the solution of any PDE are functions of several variables, okay? They are functions of several variables, okay? Good. And that the equation does not only involve those functions, but also their partial derivatives as well, okay? They also involve their partial derivatives as well. So I want us to please take note. So suppose that f is some function that is composed of x, y, u, what u partial of u with respect to x, partial of u with respect to y. You got result. So this is just the general form of a PDE. And I want to point out that the u over here we said is the unknown. Okay, we denote the u of x, y as the unknown. Okay, so we denote this as the unknown. Then the x and the y, we call them the independent variables. So please, let's take note of that. Okay, so we claim that this is the general form of the PDE, and we said that it is composed of some unknowns and their partials. Okay, and their partials. And as we can see, we have some partials here. Okay, very good, very good. Let me kind of point out that the partial of x with respect to the partial of u with respect to x can also be written as this. Okay, we would learn all of this as we move along. So I just want to, this is just an introductory part of it. So I would just want us to understand it before we move. And then what partial of u with respect to y can also be written. Can also be written as this. Okay, so let's take note. All right, now let's look at the a typical first order PDE. A typical first order PDE. So I want to also point out that the PDEs of first order only involves the solution of functions and their first partial derivative up to the first order. Up to the first order. And a typical example, let me use a different pencil. A typical example is partial of u with respect to x plus partial of u of respect to y probably is equal to 1 or probably in a 10. So this is a typical, first order PDE, okay? Because the partial is up to the first order, okay? Okay, it's just with respect to one independent variable and not multiple, okay? So that means just the solution u is the partial of the solution u is with respect to just one independent variable, and that's what we say it's the first order, okay? Now let's consider this and let's pick an example in when I kind of condense it. Suppose I have a lot of independent variables. Suppose I have, let's say I have, let's say, let me use a different pen. Suppose I have x1. Let me use a different pencil rather. I think this is too deep. Suppose I have I have x1, x2, x3, x4, up to, let's say, xn as my independent variable, right? As my independent variable. Now with this, I can use these independent variables because of that, I can just condense it, okay? Because of this, I can just condense it in this form. In this form, what we're going to do, we are summing j from 1 to n, and of which in this case, my j is the one that is summing from 1 to up to the n. Okay. In this case, my j is that. All right. I hope we are okay. All right. So if we have a PDE of this nature, what we are essentially trying to say is that the solution U, okay, so as I mentioned, U is a solution. So the solution U, exists on some domain, which is the domain exists on some subset D, and the D we said is a domain. Okay, that's where the independent variables are being derived from. Okay, and they are also contained in the Rn. Okay, the big Rn. All right, and it takes its values in R in the real number. Is that okay? And as I mentioned, the independent variables, which are x1, x up to xn, are derived from the domain. The domain we said is here. Okay. And let me also stress over here that the solution takes variables from the domain and map it onto the R. Is that okay? It takes some independent variables, or it takes some variables from D or from the domain and maps it onto the real number. Is that okay? Very good. So let's take note of that. And I also want to sort of point out that the partial of U with respect to x, we said it is read as or probably this particular notation is read as partial derivative of U at x. Okay, partial derivative of U at x, which is also taken with respect to the j coordinate xj. Okay, very good. So let's take note of that. Okay, so over here, I think that I may want to probably maybe elaborate on this a bit so that everybody would appreciate it. No, let me elaborate on this a bit. So as I mentioned that the j's are summing from 1 up to n. Okay, so suppose j is 1, in which case I'm going to replace j by 1. Okay, so when j is 1, we are going to have what? We're going to have a1 of, remember, a is a function. Remember that a is a function. So in that case, I'm going to have a1 x u of x, the partials of u with respect to x1. Okay. Then when j is 2, what do I get? When j is 2, I'm going to get what? a2 x u of x, then the partials of u with respect to x2. When j is 3, I'm going to get what? I'm going to get a3 up to the time where we get where j now is at what? N, when j is n. So in that case, we're going to have what? Your an now equal to the right-hand side there, and then the right-hand side we said is what? Equal to what? C x of u ux as well. Is that okay? So this is just, remember, each of them contains the first order. Okay, you will see that in each term we have the first order. Okay, in each term we have the first order. So let's take note of that. And that's what we said. This one is a what? It's a first order PDE. Okay. Very good. Let's take note of that. Now, I also want to say that A, as I mentioned, is a function, but A also contains another solution, which is U. Remember, our U is a solution, right? Our U is a solution. And A contains the solution and some other independent variable like the X, okay? So let's also kind of take note. Now, when we talk of an order of a PDE, what are we talking about? So the order of a PDE, over here, I want to stress that the order of a PDE is the highest derivative, okay? It's the highest derivative that appears in the equation, okay? So it's the highest derivative that appears in the equation. So in the first example, we see that the highest derivative in this equation, which is the A part, is what? Is 2. That's the second partial of U with respect to X, okay? What about the B? What would be the order of B? The order of B will be 2, okay? Because each the solution U has a second derivative, okay? Has a second derivative. The solution U has a second derivative with respect to each of the independent variables, X and T, right? Good. And what about the C? The C has order what? Order 1. The C has order 1. And the reason is simple, because the solution U is just, differentiated once with respect to each of the independent variables X and Y. Is that okay? Very good. Now, I believe at this point somebody want to kind of talk about linear PDEs. Now, what is a linear PDE? Now, suppose that we have L as an operator such that when L acts on the solution U, remember we said that U is a solution, okay? It's a solution. So suppose that L, which is an operator, acts on the U, we said that the result should be what? Should be 0, okay? When L acts on the solution, the result should be 0. So let's have that in mind. Now, we claim that the L, which we have considered, is linear if now these two properties holds. Okay, if these two properties hold. All right. Now, anytime we have two solutions, suppose U and V are some new solutions. Okay, and anytime we operate, this is what we are saying that if so, suppose U and V are solutions. Anytime the operator L acts on the sum of these two solutions, we are saying that we can have this distribution, okay? We can have this, we can just distribute. So in the B part, anytime we also pick any scalar quantity, let's call it C, and we multiply by any solution at all, let's call the solution U, then anytime the operator acts on this term, we can quickly, write the C behind, or you can just allow the C to multiply the solution, okay, or the result when we make L to act on the solution U. Okay, good. So let's take note of that. Very, very important. Now at this point, I want her to solve some one or two problems. Then we see how best we can go from there. All right, so we want to determine whether this PDE is linear. We want to determine whether this PDE is linear. All right, so let's move on. So for us to determine whether this PDE is linear, there are two properties we need to meet, or there are two conditions we have to meet, right? One, so the first thing to do is that we want to assume two functions, right? Suppose that U and V are some U and V are some functions, and C is a scalar. Okay? Suppose that U and V are some functions and C is a scalar. Now, according to the first property, if L is an operator, then we said that anytime the operator acts on the sum of the two solutions, we shall have what? LU plus LV. Is that okay? Good. Now, this is what we are going to do. Now, suppose we have some function, let's say F, big F, okay? So let's say we have some big F. Now, when we operate that on this, okay, when we operate that on this particular problem on the left side of the problem, when we operate that on the left part of the problem, we are going to have. So we are going to have, okay, let me just do something here. So before we start that, let me do a quick review over here. Okay, let me do a quick review over here. So I can just say that, so my U, the partial of U with respect to X equal to 0. So this can also be written as what? This can also be written as this, right? This can also be written as this, right? Good. So if this can also be written as this, then we can just go straight forward, then we solve it. Is that okay? Very good. So let's take note of that. All right. So if I have some function, let's call it F. Let's call it some big F, okay? Now, anytime we operate L on this F, then we say that we can write it this way based on the given problem, based on the given PDE. We can write this as what? The partial of F with respect to T minus the second partial of F with respect to X. Okay? Very good. So if that is the case, remember F is also a solution to this. If F is a solution to this, then we can also have this, right? Are we all getting it? If X is, suppose F is a solution to this. If F is a solution to this, it means that we can also write it this way. Is that okay? Good. So on that note, now let's go back to what we are doing. Now look at the property. Now, when we operate the L on U plus V, it also means that, remember, U and V are also solutions. So when we do the same, when the operator acts on the sum of these two solutions, we can also write it as this. Is that okay? So on that note, we're going to have the partial of U plus V with respect to what? T minus what? The second partial of what? U plus V with respect to what? X. Now, we said that we can distribute. If we can distribute, it means we can have what? The partial of what? U with respect to T plus the partial of what? V with respect to T minus the second partial of U with respect to X minus the second partial of V with respect to what? X. Is that okay? And at this point, what I want her to do is that we are going to group the U's and the V's, okay? We are going to separate the U's from the V's. So you have one U here, another U here. So let's put them together. So on that note, we're going to have what? This partial of, now let's the partial of U with respect to T minus the second partial of U with respect to what? Then let's also, group the V's, right? So we have one here and then here. So we're going to have the partial V with respect to T minus the second partial of V with respect to X. Now let's convert this back to the way the solution was looking at, okay? So on that note, this can also be written as what? UT minus what? U xx plus what? Vt minus what? Vxx. Now, what can we say about this? What can we say about this? This is our what? What can we say about this? This becomes our what? This becomes our what? Our LU. Is that okay? And what about this one? This becomes our what? Our LV, right? If that's the case, it means that we've been able to satisfy um, um, the given property. Now, the first property, we've been able to satisfy that, right? Is that okay? Good, 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 good. So let's move on. Let's move on. Now, the last property, so you're done with the A part. Now, the B property or the last property is that we have C as a constant. So given the constant, so given in a scalar, let's call C, then anytime we act the operator on such, then we should get something like what? Good. So now let's start with this. So this means that wherever, so let me write the solution here, the given problem again here, so that we can refer to it. So the given problem was on ut minus uxx equal to 0. Okay. Now, this means that wherever I see u, I should just replace it by this, Is that okay? So on that note, I'm going to have what? See u. So with this, I'm just going straight forward because now you are familiar with what I'm doing. And wherever I see u here, I just replace it by that, right? Is that okay? So I'm u. All right. So this can, because now we have C, which is common to that, we can factorize the C out, okay? And I know you're going to have ut minus what? Uxx. Now, what is this? What can we say about this? This is your hot, your L hot, LU. So in that case, we're going to have what? C multiplying the operator acting on U. Now, what can we say? Now we've been able to satisfy the two properties, okay? So now we have that what? So now we can say that, so now, or does, we have that does the PDE is what? It's linear. Good, good. So it's now linear. So let's take note of that. Now let's look at one more example, then we see how best we can handle that. One more example. Is it always the case that every PDE is linear? Let's look at this example. Let's see whether this example would maybe say that not every PDE is indeed linear. Maybe this particular example would counter it. So let's see how it goes. So for us to determine whether this PD is linear, we have to come out with some two solutions, right? Good. So suppose that U and V are some solutions, okay? Are some solutions or are some functions. Let me put it that way. Are some functions. And C is a scalar. And C is a scalar. So if that's the case, we have to satisfy the two properties, right? So it means L acting on the sum should give us what? LU plus LV. Is that okay? Now I think now we have grown in it, so I'm not going to introduce anything. So I'm just going straight forward because now I've introduced two new stuff, so I'm just going straight forward. All right. So in that case, when L acts when L acts on this sum, it just means wherever I see U over here, I can just replace it by U plus V. Is that okay? When we when L acts on this, we are going to have, so it means wherever I see U, just replace it by U plus V. Is that okay? So let's do it straight away. With respect to X, is that okay? Then plus, we have U, and the U, our U is now what? U plus V. Then we have our what? U plus what? V partial. Is that okay? We are only considering the left-hand side of the PDE. So let's take note of that. All right, so on that note, we can do our distribution, right? So when we distribute the partial, this can be written as what? Ux plus what? V what? Vx plus what? Now over here, we also have to distribute as well. So we also have U multiplying, let me take my time so that I think at this point, I would have to really take my time so that I don't cause trouble. We will come back to this, but let me really take my time so that everybody would appreciate what we are doing. So this particular solution, we are looking at the left-hand side of the solution. So we are looking at this, the left-hand side. So I want us to write in a different form. So by writing in a different form, we're going to have, we are going to have, by writing in a different form, we're going to have the partial of U plus V plus U. Our U is what? Is U plus V. Is that okay? Then the partial of U with respect to T gives us what? U plus V with respect to T. Is that okay? Very good. Now let's distribute. By distributing, we should have the partial of U with respect to X plus the partial of V with respect to X plus, when we distribute this, we should have what? U multiplying the partial of U with respect to T plus U multiplying V, U multiplying the partial of V with respect to T. We are just distributing this, okay? So that's all that we are doing. And then V multiplying the partial of U with respect to T, and then V multiplying the partial of V with respect to T. Is that okay? Very important. Now, at this point, what that we need to do is to group the U's, okay? At this point, we just have to group the U's. So we have one U here, another U, and the where? Another U here. Oh, no. And that another U over here, the partials on all of them. So let's try and group them. So we have, so now let's convert it back into the other form, okay? So over here we have what? Ux, we have what? U multiplying partial T, and then we have V multiplying U partial T. Please, are we okay? All right. So on that, what about the other one? So we with the V's, we have this, we have that and that. All right. So on that note, we're going to have the V partial, the partial V partial V with respect to X, and we also have U partial V with respect to T, and then we also have what? V partial V with respect to what? T. Now at this point, let's see what we can do. Now we have the U's and then the V's. Let's see how best we can, deduce our LU and that of our LV from that. Now, what can we say over here? So when we look at the U's, does it look like the solution or the problem that we're given to solve, or the PDE? Remember, we were giving this as a PDE. We're giving what? The partial. We're giving this to, so where is it? We're giving what is it? The partial of U with respect to X plus what? The partial of the u multiplying the partial of what? Partial of u with respect to t equal to 0, right? But can we find the left-hand side of this PDE over here? So we kind of see that we only have this at this side. We only have that. Then we also have this in terms of v. We also have it over here. But there are extra terms that cannot be found in this PDE. You know, extra terms like v multiplying u of t, v multiplying the partial u with respect to t, and then v multiplying the partial v with respect to t. All of these cannot be found. All of these, they cannot be found over here. And because they cannot be found in this particular PDE, we claim that such PDE is not linear. Is that okay? So over here, we claim that this is not the same as what LV. So on that note, we have that. So therefore, the given PDE is not linear. Okay. So over here, this example has sort of, pointed out that not every PDE is linear. So let's take note. This is a typical example of a PDE that really shows that not every PDE is linear. So please, let's take note of that. At this point, if you have not subscribed, please do so. Like, comment, and share my content to other colleagues, loved ones, and let's help demystify the myth around mathematics. All right, let's move on. So let's cut the last problem before probably maybe we take a break. All right, so with a third example, when I also want to determine whether this PDE is linear. So the partial of x, the partial of u with respect to x plus the partial of u with respect to y plus 1 equals 0. We're not sure whether this PDE is indeed linear. Is it the case? If I were you, I'll just pause the video, try it on your own, then you compare your result to mine. All right, let's get started. Suppose we have two functions. Suppose that u and v are some functions, okay? And c is a scalar, okay? All right. And according to the property, suppose we have a linear operator. Suppose that L is a linear operator. If L is a linear operator, then the following property or condition must be met. Then when L acts on U plus V, remember U and V, there are some functions. When anytime the L, which is the operator, acts on the sum of the two solutions or two functions, you should have the distribution as this. Is that okay? Very good. Now, that's the A part. That's the A part. So how do we solve this? How do we solve this? Now, so if I have L operating on the sum of the functions, now what you're going to do is that we are going to consider the left-hand side of this PDE. So by considering the left-hand side of this PDE, we kind of assume that wherever I see U, I should just replace it by what? I should just replace it by U plus V. Is that okay? Wherever I see U, I should just replace it by U plus V. That's the easiest way. Somebody want to go straight that way. Okay. Or you can just take your time and solve it like the first thing the way I took my time to go through the first example that we solved. Okay. Otherwise, you can just go straight forward like that. Good. So on that note, we are going to have what? So over here, what happens over here? Wherever I see U, I should just replace it by U plus V. Okay. So if that's the case, we're going to have what? U plus V, the partial of U plus V with respect to x plus the partial of U plus V with respect to y plus 1. Okay, we only consider the left-hand side. We don't consider the right. We only consider the left-hand side. Okay, now let's do our distribution. So by distributing, we're going to have what? By distributing, we're going to have what? The partial of u with respect to x plus the partial of what? V with respect to x, the partial of u with respect to y, the partial of v with respect to y plus 1. Okay? Now let's try and group the u's and the v's. Okay? So we have one u here, another u here. We have one v here and another v here. Okay? So let's group them. So on that note, we're going to have u, let's put the u's in one bracket and the v's in another bracket. Now, you see, let's look at something here. The main problem, we were given this as our main problem. Our main problem was u of x plus the partial of u with respect to x plus the partial of u with respect to 1, y plus 1 equal to what? 0, right? But is it a case that we can, really point out that such equation would satisfy this? We see that the partial of u with respect to x plus the partial of u with respect to y, it's like something is missing over here. We don't have the plus 1 over here, right? The plus 1 is missing here. The plus 1 is missing over here. We also have plus 1 missing over here. We only have plus 1 outside. So, we only have one thing that is missing, which is another plus 1, So for this particular equation to satisfy this, we need another plus 1, but we don't have that, right? Where we can just, if this 1 was to be 2, then we could have distributed it so that we can, this particular, equation or system would satisfy this. But since we do not have that, we claim that such PDE can never be linear, okay? So this implies that the left-hand side can never be equal to LU plus LV. Is that okay? So on so does what? Does this PDE, the given PDE is not what? It's not what? It's not linear. Okay? And at this point, if you have not subscribed, please do so. Share my content with your colleagues, with your loved ones, and let's help demystify the myth around mathematics. All right, stay blessed.